Hi everyone, welcome to the first NLG seminar of 2026. Today we have Wang Zhu. Wang Zhu is a final year PhD candidate in computer science at USC, advised by Jesse Thomason and Robin Jia. His research lies at the intersection of NLP, machine learning, and vision language reasoning, with a focus on neuro-symbolic methods. He previously conducted research at Meta Reality Labs and Google DeepMind. Bill has published extensively at top-tier venues including NeurIPS, iClear, NACL, EMNLP, CBPR, and ACL. He actively serves as a reviewer and area chair across NLP, machine learning, computer vision, and robotics venues. He's a recipient of the NSF Access Computing Grant.
Thank you. Thank you, DJ. Yeah, good afternoon, everyone. I'm Bill, and I'm a final year PhD candidate at USC now. And today is my privilege here to talk at ISI to share my research on a paradigm I call domain adaptive programming. So I've witnessed the rapid evolution of language models through my PhD from word-to-vector, BERT, GPT-3, T5 to GPT-4. And I started my PhD in the middle, like on 2021. And we're currently standing at an inflection point. Large language models have demonstrated unprecedented capabilities in general tasks and have been applied to many fields, including healthcare, finance, education, software engineering, laws, and science. However, as we push these models to specialize high-stake domains like robotics, healthcare, and complex system engineering, we encounter a persistent war of brittleness. That is, language models intended to fail on like hallucination issues, on sycophancy, etc. So today I will introduce my frameworks that bridge that war and to build verifiable language model systems, not by making the models bigger, but by making them structured. We will explore how grounding neural reasoning in formal programs allow us to expand the boundary of what language model can reliably solve. As we said, the current power of language model allow us to shift the paradigm from single round, which only takes the input and context as like a language model context and generate output, to a more sophisticated multi-round and iterative setup, which can involve an executor and which provide the arrow of the output and probably an expander on expanding what the arrows are. The expander probably like interact with some kind of memory systems to start the failure cases. And then we have a stopping criteria on whether we should like keep the loop or provide a final answer. But no matter single round iterative is usually with like limited data. When we try to solve a new task, we're not like trying to always talking about pre-training a new model for a specialized domain. So to solve this, I borrow a word from domain adaptive pre-training and propose domain adaptive programming. This paradigm fundamentally changed the role of language model. Instead of asking model to be the final solver, we optimize to act as a translator or architect. We task the language model with generating formal symbolic structure and replacing the output with symbolic structures. And that can be a chain of logical sub-questions, a PDL domain file for a robot, or structured user profile. And by grounding neural reasoning in these formal structures, we achieve the best of both worlds, the infinite flexibility of neural network to handle massive natural languages, coupled with the rigorous guarantee of symbolic system. So we don't ask the model to think, we force it to program its reasons in language that we can verify. So in this talk, I'll talk about how can we do domain adaptive programming, where to apply domain adaptive programming, and what do we need for domain adaptive programming. So first, how should we actually do the domain adaptive programming? There are two different main strategies me and like the community employ. First, we can use symbolic structure as intermediate reasoning steps. For example, we ask the model to predict programs or structural output before arriving at a final answer. But we want to use this program to do execution or to do verification. The representative work like a program or sort or prog prompt. And the second one is we also use these programs as verification tools to ground both intermediate steps and the final result. I've applied these two strategies across several works as leading author. But today I would like to highlight SOM and SOM-V, which leverage programs as verification tools in the planning domain. So before our work in the planning domain, there were two main paradigms. First, we had language models, which generate plans cheaply with vast common sense, but are noisy and prone to hallucination, even with programmatic assistance like a programmer thought. Generated plans often fail to meet action preconditions or attempted on incompatible objects. On the other hand, we have symbolic reasoning or planning. And while it offers reliable actions, it requires expensive domain knowledge, and which is always expert specified. So we need human to write down the rules for the word model, for the knowledge to set up. And before introducing the actual idea, I'd like to briefly introduce the symbolic planning using PDDL. We have a domain file which has the predicates. That is how the state will be like in the environment. And we have a list of actions with action name, action parameters, pre and post conditions. The precondition is a condition that the action has to map before executing. And the effect is what the state will change after executing the action. And we have a problem file which defines what the objects are in the environment and what's the initial and goal state. So to visualize this problem file into the block stacking problem, we want to like transfer the initial state to the goal state by changing the order of blocks. And given the domain and problem file, there is a symbolic solver, which is essentially a graph searching algorithm. And it takes the initial state and search through the graph and doing heuristic search to find a path that execute from initial state to the goal state. And assuming time is unlimited, through this abstraction, we are guaranteed to find the ground truth solution of a plan if we have the correct domain and problem file. So do we have to choose between these two strategies? It's a clear no. We should take the benefits of both, which language model generates cheaply defined domain file, and the symbolic solver can generate perfect plans given provided a correct domain file. And this is like our work published at NACO 2025, predicting semantics of action with large language model. And the insight is we use language model to iterative guess the domain. You can think of it as a word model based on the execution trace for attempted plans. And the input is a problem file and a domain file with no action semantics. So we have to provide what actions is actionable in the environment, but we don't know what are the conditions and what are the effects to execute them. So the key element here is the probabilistic memory of action semantics, which is updated from Lang model predicting the feedback from execution. So we give each class a probabilistic value in the memory. For example, for put down object, the probability of holding object as a precondition is like 0.9, and the effect of like not arm empty is 0.1.
Sorry, are those each binary variables that could be true or not true?
Yes, yes. In the actual domain files, they're actually like binary values.
And are they like all orthogonal from each other? No, they're clearly not, because arm empty and not arm empty are not both possibly true.
Opposite can both exist in the memory. Yeah.
But then shouldn't, I'm looking for distributions and not seeing them. For example, shouldn't arm empty and not arm empty add up to 100?
No, they're independent, but they just like, yeah. If you pick both, that it's a clear failure, and then there will be feedback to update it.
Well, sorry, you're learning these.
Yeah, we are learning this. We're updating this. Yeah, by updating memory from a sample domain file, the word model from we learn actual domain file. Yeah, from the.
Are these predefined possible actions? Like the holding on table, is that like a list of candidates?
These are the predicates that are the clauses, the like states that exist in the environment. It's predefined. Yes, we have to give this, otherwise it's not.
Yeah.
It cannot enable our learning.
I mean, should there also be a not on table, or is that just the way you define it is?
Oh no, this is learned. This is like what Lang model predicted. So we are not sure what.
But the fundamental components, holding, clear, untable, arm empty, those are also guessed at, or is that provided?
That is provided in here.
Like the template, essentially.
It's provided as the predicates as the header of the domain. Yes, got it.
It's a header file without a CPP file.
But without the object fielding, there's a question mark X. Yes. So we can eventually derive a crack word model to replace human effort and thus to achieve robust planning with a sample domain file. Yeah. So what's the role of the Lang model here? So first, as an idea proposer, I utilize the Lang model's common sense reasoning ability to propose new plans, as well as hypothesis new semantics. So Lang model is doing like these two jobs. So if we look at the whole picture, it's like a pretty complex system. So first, we have a Lang model trajectory sampler, which samples trajectory given the domain info and the problem info. So it can be a broken domain file, yeah, but you need to sample like a plan given, and then we execute these plans in a textual environment, and the textual environment will give us detailed, rich feedback on which step it is wrong and where it is wrong, and where we should fix, and then we use this feedback and as input to an action semantic predictor to provide the action semantics, that is what is the precondition for action A, what is the precondition for action B. There's two n runs where n is the number of actions in the environment. And we have a hypothesized action semantics to update the memory. The memory is updated in exponential forgetting rule. So if there's no, if it's not predicted by the Lang model for run n, and the value in run n -1 will be like forgetting by a factor of 0.99. Yeah, and if it is, it's updating. Yeah, the probability will goes up. And then we sample probabilities using binary sample of the precondition and postcondition to construct a domain file and give it to the symbolic solver. So if this domain file is correct, then there is a solution. Otherwise, there's no solution. We have to give this partial search result of the tree search from the symbolic solver to the language model as feedback. Yes.
Is it not possible for it to construct a world model that has an incorrect solution? So it thinks that it's able to terminate, but actually it's gotten it wrong.
Yes, there is possibility that it is providing a solution, but the environment is not successful on executing this solution. In this way, we have a successful plan. We have a partial plan, so we can skip the planning stage, and we just directly provide the plan, the broken plan, to the action semantic predictor again to do a smaller loop. So in this way, yeah, we update the memory from the smaller loop, and it is almost correct, but there is something wrong in it. Yes. Through this algorithm, some can recover action semantics across different domains and backbone language models up to 100% on 7 IPC domains like Bloxworth, Barman. These are like the international planning competition tasks. And we can see that through different ablations, if you drop different component, the efficiency of the algorithm will goes down. So so you can see, for example, if you drop the language model action semantic predictor, the execution steps will rise from 200 steps to 600 steps to recover the whole action semantics. Yes, and we see that it's not only like a GPT-4. We use like the like top tier models, the prompt tier models to do this task. We can also do this task with Mistral 7B, which is a very like yeah, I should not say it's an old model, but it's a medium-sized model now. Yeah.
Sorry, what does NR and NAS mean again?
The NR is the number of resets. The NUS is the number of executed steps. It's basically with more like time, but you can still recover it to 100%. These are all like 100%, but just with like more time. Yeah.
I still don't.
So you need
is it better to have more or fewer of these things?
Sorry.
What is the takeaway from the graph on the right?
So we can use 3 models to recover the domain, but with weaker models, we need more iterations of language models to recover the
okay, so domain. These are cases where you're saying that for the termis or whatever it is test, it's what does it take to get to 100? To get to full coverage, fully having learned the logic.
Yes, so it takes like termis has like 7 actions and like each action have like 5 or 4 clauses of action semantics, and for GPT-4 we only need like 20 rounds, 20 iterations for language model, 20 resets. So yeah, it's think of it as a robust, so it's like reset to the initial state. And for Mistral, we need like around 25, but yeah.
Mistral's cheaper, yeah. So probably better to use.
Yeah.
Were there any cases where you couldn't learn everything?
No, it's in text domain, we have very rich feedback. We have like the signal of which step you're actually wrong and what action, what precondition you're actually not met. So it's very easy to do this like probabilistic learning and fixed errors. So you can always have some progress, even with a rule-based system, right?
But you get to determine the signature to begin with, right? Like what the functions essentially that you're building are?
They have because if you fail on like action pickup, that means the precondition of pickup is wrong, right? So you need to.
I'm saying the pickup is a thing that you. I mean, maybe you could say that it's these data sets that create them, but essentially you get to say like pickup is a thing we want to learn.
Yeah.
Right. And so you have coverage once you've completely learned pickup.
Right.
Once you've learned the body of pickup, essentially. So, right, it could be like you could have, for example, in Block's world, like make a $sign as one of your functions, which is a much harder function to learn.
Yeah. The signature is important. It's provided by the original data set. Yeah. If we use a different signature, then yeah, we haven't tried. Yeah.
So, but everything that you've actually tried it on, which is these 7 things, presumably,
yes,
you've learned at 100%.
Yeah.
You've never gotten to any kind of like speculative data set. They were like, maybe let's try it. It's a super hard challenge, and you couldn't learn it.
We failed on the later tasks like afterward. I'll tell you later.
Sorry.
I'll tell you later. And because so like in this idea, the language model and symbolic reasoning are complementary. So we take the best of both worlds. But we have made some pretty unhinged assumptions. So first, we don't have visual observations. So everything is provided in text, and the state is very accurate. And second, the action effects is like, okay, we always have the arrow match very accurately. We don't have like a failures that are vague. For example, in Afro, you execute, you hit a wall, there's no arrows. You just cannot move, right? So for these things, we fix in the later work by using language model to estimate the state of word at each time step and reason about changes caused by the action and guess why the error occurs. So we do visual sum, where we first do a full exploration of the environment and through several time steps and build a infer semantic map, which we use GPT-4o to translate into a problem file. So we don't have any problem file at the start, but we need to create one. And because we don't know the locations, so we also construct a location map to map to locations at different time frame to the location of objects. Yeah, so you know where the objects are. And the key part of the visual sum is there's a small problem file checker here, which iterative check the problem file and make sure it is correct. That's like another small loop. But most important thing is here. There is error predictor. So we look at the visual feedback of the failure in execution, and we predict why it is failing by GPT-4o, and we'll have two types of different errors. First is there's an unsatisfied precondition. Some precondition is not satisfied for action pickup, so we cannot move on. And the second is everything is correct, but go is not reached. You just didn't finish the plan, so your plan is stop in the middle. And what is the missing go conditions that you didn't achieve? So, for example, you want to pick up a cup of glass, and then you also want to turn on the light. So there are two tasks. If you finish one and not finishing the other, there's like one missing part here. And through this technique, we can see that in two different gaming environment, Alfred and Overcooked AI, there's improvement over like just large vision language models on Cloud 3.7, which was the best model at that time, and GPT-4o.
What's your approach to the this? You're doing a bunch of environmental looking around at first, right?
Yeah.
So what is your general approach to doing that?
It's a semantic map creation strategy, which called like firm. Yeah.
What is that?
That is like you explore the environment and you take a like snapshot on each time step, and then you do a fusion, vision fusion.
Oh, you're saying just to form the space, but in terms of so you're just mostly interested in like walking around and seeing the environment.
Yeah.
No, not interacting with the environment.
Interacting is in the actual stage of like doing the tasks. Yeah.
Okay.
And then you can learn the action like pick up and like turn off the lights. Yeah.
But what the actions like move left and move right? Are those kind of baked in?
Those are not baking. Those are learned.
You have to learn them.
Yeah.
So what's to stop from like how do you get around like just kind of staying in place or doing nonsense continuously?
Oh, actually, we have extracted the move left and move right to a meta action called go to. So we just do go to locations, and then it's kind of like we'll go to any of the locations of the objects.
Or you have the locations.
Yeah. So there's a lower level navigator that performs this like navigation.
So you can do go to of a set number of locations.
Yes.
And the go to will go in the most direct way.
It's shortest path.
Which means that you may miss some of the map. And so
that's true. That's true. Yes.
And thus you need to like, basically try all possible pairs of going in order to kind of cover as much map as possible.
In the initial exploration, we do like a full exploration and
all possible pairs.
Yes, and in the later refinement stage, we just try the task. So we only care about the small. Like if you're just in the kitchen, we care about the task in the kitchen. Yes. These are like details. Yeah. Good questions. But yeah. And we also perform this like block stacking task on the real robot. This is like a video demo, which the first round it fails because it put the blue on top of orange, and when it's not learning the environments like action semantics in the first stage, but in the second stage it fixes it, it learns it. And
why does the light keep on changing?
Oh, because we piece together the video. It's like frame by frame, and we merge it.
Is it a very, very slow process?
Yes, very slow.
So is that because we're seeing the sunrise and set over and over again?
Yeah, it's just like overall the video here is like 5 minutes, and I compress it to like 5 seconds.
Oh, 5 minutes shouldn't cause the light to change that much, right?
I don't know. It's a light from the there's a light from the top, and the arm moves and the light change. I think because there's different like because video have different setups. I think it's like there is a different setting on the cameras in each round.
This is just execution, right?
This is just execution. This is learning and execution. So okay. Yeah, this is learning and execution.
Wait, that arm is learning?
We are executing, and then we are learning a domain file, which I didn't show here. And you can see the first stage is run because it learns a run domain file. Yeah. And when it learns a write domain file, it is continuous. Yeah.
And what would you say is the main bottleneck for why it's so slow? Is it the vision language model side, or is it the like?
Why it's so slow? It's a low level control of the robotics.
Okay.
I think it's hard to do that kind of fine grained pickup fast, right?
Mm-hmm. It need to be very careful because if you just do it very fast, it's likely to crash the.
I guess you already published the paper, so it's not, it's not really worth regenerating. But like if you're showing this at, talks for whatever reason, like it would be probably better to try to control the light because it's hard to watch.
I see. Yeah, makes sense.
If you're, I don't know, if you're getting a job or try to sell your business.
Thank you. Good advice. Yes. Yes. Let me summarize how to do domain-adaptive programming. So one important thing is we need to interpret these domain-specific arrows as signals to meaningful feedbacks. So we have rich feedback from the textual domains that are easy to interpret, and we have visual feedbacks that is like sparse and hard to interpret. This requires different designs to like make it meaningful. And we also have this memory. I feel it's pretty important to probabilistically filter the language model proposal, because language model proposals are like it's noisy and it's likely to hallucinate. So you need to use some like a fusing mechanism to like filter it. So yeah, we finished the first part, and let's go to the second part, and where to apply domain adaptive programming. It is very clear, like on domains that requires verifiability and complex reasoning. But what else? I'll shift our eye to like benchmark creation. So many benchmarks claims to be testing the reasoning. For example, the ArcAGI, the visual logic, and the MMTOM-QA. But are they really testing these like the correct reasoning they want to test? I want to choose this serial mind test as an example. First, I want to introduce the SETI-N paradigm if people are not familiar with the serial mind test. So you, as a person, SETI, was in a room and you saw a ball on the table. And then you move out of the room. There's a person N, enter the room secretly and put ball under the table. So the job is to predict whether SETI will think the ball is still on the table, or she will think the ball is under the table. So from her previous observation, the ball should be still on the table because she didn't see the person N to put this under the table. And language models are like evaluate on these kind of tasks. And if we make things more complicated by adding more number of rooms and more actions, and ask like some questions relevant to it, the language model will likely to be wrong. For example, if we ask the question like, which is more likely to be true? N has been trying to get a wine bottle from this kind of narrative. And we can see that from the actions, N proceed to the kitchen and approach to the first kitchen cabinet and opens it, and subsequently close it. But we also notice there is a wine bottle in the first cabinet. So if she's trying to find the wine bottle, she should not close the first cabinet. And then we can infer that N has been trying to get a salmon is more likely to be true.
Disagree?
Okay.
I would say that Anne I would say it's still more likely that Anne's been trying to get a wine bottle, just not that wine bottle. Because why would you look for a salmon in a non-refrigerated space?
But that's how the data set created. I think, yeah, there is a fridge. There is a fridge. Yeah.
There's what?
I don't know. Yeah, that's how the data set created.
Okay.
There's like they think it's kind of like counterfactual reasoning and belief reasoning. And
okay. Do you know how the data set was created?
The data set is created by like videos, I think. Yeah, the videos. There's actual.
Well, I mean specifically the intent of the wine bottle versus salmon. Where did the word salmon come from?
The salmon is nowhere. It's not mentioned in the environment.
Right. So how was the data set created?
The data set is created by like evaluating human, I think. Yeah.
By what?
Evaluating human.
Oh, human.
Yeah.
So there was an actual Anne who they asked, what did you want?
There is a simulated environment, and they ask human to answer these questions.
Okay.
It's more like an accurate environment. Yeah.
I see.
And people have different beliefs on why language model suffers. And first is like they think language models don't have this enough belief and counterfactual reasoning ability. There are several papers on this. And the second is several people believe that models have like lack of state tracking ability, and we should improve state tracking and to make like serial mind tasks better. But there's debate on these two, and there's no single conclusion we can draw from this. So what we do is we use introduce a method called PDO mine, which disentangle the reliable reasoning with state tracking and try to illustrate that this serial mind task is heavily relying on state tracking. So what are we doing? We begin with a predefined PDL domain file. We manually write it. There's like 4 different main predicates. Where is the agent at? Where is the object hierarchical? It's like which object in which object, in which room, and what is the object seen by the agent at which location, and what is the utterance heard by the object by the agent. So it covers mostly all the scenarios in those interactive serial mind tasks and also conversational serial mind tasks. And there are 7 actions, but very simple, like just like move, open, close, these like put, drops, these things. And we first, from this predefined domain file and narrative, we parse the environment into objects and initial state. For example, Anne is at the bathroom. There is a statement saying like Anne is in the bathroom, started from actions. And then from the domain file and problem file, we predict the action sequence by parsing the actions into sequences. Like Anne moved to the kitchen and Anne opened the cabinet, for example. Now, most importantly, we have a verification stage by actually verify which actions are valid actions in this predicted action sequence, because the language model can make errors in parsing, right? And there can be, okay, M move to the first cabinet, or M move to the coffee table, but these are not real actions that are defined by the domain file as valid, because the move action can only move to a place, not an object. So after we do the verification state, we have a very clean set of object and actions and states. And the verified state is like, okay, when N is doing a move action, what is where is any at, and what is anything, and what is N heard? And we have a list of these states. And finally, we put this state back to the language model with the serial mind questions and have a final answer based on it.
I mean, so assuming this is the same narrative as before, or the same theory mind question as before, and now I'll accept the reality that because there was a wine bottle scene, it must be a salmon. Where, like, it seems like this whole kind of procedure is just meant to very clearly and like with high precision, get your list of actions and states. But the common sense aspect of, because I saw a wine bottle, if a thing that I've seen is in the list of things that I might want and I didn't pick it up, that it must be the other thing, like to fill in the hole. Like, why would this kind of like refinement lead to an improvement of the answer?
Yes, exactly. So this is the second. This is the first hypothesis, right? If model is bad on counterfactual reasoning, then this might then even with state tracking like this, good state tracking like this, the model might fail. Right? If model is good on the counterfactual and belief reasoning, then with this like reliable enough state tracking, the model will will answer the right question.
Oh, so what you're saying is the model is good at counterfactual. Counterfactuals. The only issue is just the noise of the states.
Yeah, we will see. We'll see.
I'm going too fast. Yeah.
Yes, this is how the results are in 2 different benchmarks, MM-Tom QA and MUMA. Indeed, as John just said, humans are worse on the MM-Tom.
Peter, do you know what's going on? Peter.
I just hibernated. Let's try to read.
Did I become that? reconnect.
Yeah.
Oh. Yeah, what's happening?
Maybe my computer should change. I should buy a new laptop.
And this happens more often than it should.
Really? This hasn't happened yet, right?
I've seen it. I don't remember.
Peter, any idea what's it says?
Try it again.
Yeah.
Okay, good. So yeah. People always say, okay, there are a lot of gaps between language model and different methods and to human performance on these tasks. But we can see by state tracking, we reduce the gap by large, and there's only like 12% of errors here. And yes, indeed, as John said, this like MM-Tom data set, human performance is not perfect on that.
So which is the equivalent where you're not cleaning up the state tracking?
Yes.
Is it GPT-4o or?
We're GPT-4 end-to-end is like the direct inference of.
So yeah, you're using GPT-4o, but
Yeah,
you're
we're
doing state
doing
tracking,
both-
state
both
tracking
with
cleaning.
state, yes.
That's a huge gap.
And we analyze this 12% of errors manually by looking at 20% of data, 20 examples per data set. And we notice that the parsing errors, that is, the PDL parsing is wrong, and the verified action and state are wrong, actually by our manual inspection. It's 33%. It's like one third of them. And the reasoning errors is like 67%, which the model derived the wrong answer from the correct state tracking. And that means, assuming we have perfect state tracking, GPT-4 can achieve like 92% on both benchmarks, which is very close to human on 93.5%.
Do you know what the gap on humans is caused by?
I think probably perception. I mean,
it could also be poorly phrased questions or things like that.
Yeah. I think the question probably not phrased well. Yes, and that means state tracking is the main factor, and we should not claim language model is bad on belief reasoning and counterfactual reasoning, but we should claim language model have no state tracking ability, and that is the main factor of why this language model fails on serial mind tasks. So where to adapt, like apply this domain adaptive programming, except domains require verifiability and complex reasoning. We can also disentangle state tracking from reasoning in benchmark creation, and like the reasoning benchmark creator should try this to make sure their benchmark is really testing on what they're trying to benchmark. Yes. So finally, what do we need for domain adaptive programming? I'll talk about this ongoing work. We code generation and debugging. So for sure, we want to generate symbolic programs. The code generation and debugging ability are very important. But which one is more important? For sure, debugging, because we only do code generation once, and we do debugging multiple times, and it's very hard to generate code like correctly at once. Because in the first stage, there might be some missing infos, there might be partial observability, etc. And imagine what if we ask language model to generate PDL domain file without actually feedback. So we just ask language model to generate the domain file iteratively and give it a feedback on you're right, you're wrong. And we do the same block stacking task on full meaning. In the first stage, there's only one action, out of the 4 actions, there's only one action stack is wrong on one class. So there's a minor error. And when we ask the language model to debug it, there are more errors. The second step, the unstack action is wrong on one class. And as you debug more and more, it's spreading like a virus. Everything is wrong now. So it means the language model has very low debugging ability, and it has the wrong debugging focus because it cannot debug the right thing. It is it should debug on, and it is doing something else. So now you might wonder, oh, it's 4 minutes. It's not the best model. And I'll tell you, the best models are also doing things wrong in a different way. So if I ask the top model, which is GPT 5.1 Codex, which we think of as the best coding model now, on a simple task on binary search with 2 arrows. One is off by 1 arrow in line 3. One is a tracking arrow in line 10. The model is doing like a completely regeneration. It's not doing debugging. It is regenerating the whole code. And the precision is very low. It only cracked the crack arrows in 1 line, and all other lines are like regenerations. But it is cracked. So to doing precise debugging, we wanted to say, okay, we only fix these 2 lines that is erroneous. So what is the problem in current benchmark coding benchmark evaluations that cause this? So all the coding tests are now based on unit tests, which means these 2 different debugging of the previous binary search is give a score of 1 because they all passed the unit tests. And these 2, which one fix no code and introduce another bug, and the second one fix partially the code, should all get a score of 0 because they didn't pass the unit test. And to solve this issue, we propose a precision debugging benchmarking framework, which turns any code completion data into a precise debugging benchmark, and evaluates them on precision, edit level precision, and bug level recall, and unit test pass rate. So how do we achieve this? So first, we have existing coding benchmark with tasks and ground truth solutions. And we pass through a language model to generate 1-line bugs, multiple ones, which consists of 3 different operations and 5 types of bugs. 3 operations are, you can remove a line, you can insert a line, you can substitute a line. And for 5 different type bugs, they are like orthogonal defect classification bugs. So they're general across all type of different programming languages. They're assignment bugs. So you assign a wrong arrow, a wrong value to a variable. They're tracking arrows. You are like probably doing a tracking condition wrong by missing some tracking conditions or doing a wrong check. I think on the right, the line 4 and line 10 are all like tracking arrows, because the first one is the tracking is off by 1, and the second one in line 10 is missing a check. And their algorithm arrows is like the reasoning arrows on the algorithm. The algorithm itself is wrong. And there are also build, package, and merge arrows. It's kind of like the version arrow, or you are calling the wrong classes or wrong methods that doesn't exist in the class. And finally, there's timing and serialization error, which means your algorithm takes much more time than expected, and it would likely to have a timeout. And the serialization and like parallelism is wrong. Yeah. And after we generate these different types of one-line bugs, we will verify these bugs are actual bugs by unit tests. And then we do bug composition based on the edits. So we have multiple bugs in one bugs in one code snippet. In this way, we have a buggy program with the ground truth line edits, which we generate the bugs from. And in evaluation time, we have a ground truth line edits as we generated, and we ask the model to debug the program and generate this predicted line edits. We first match this predicted line edits to ground truth line edits with a kind of a variation of nearest neighbor algorithm by matching the blocks of edits to the line edits in the ground truth line edits. So each block of edits, which is consecutive edits in the predicted edits, is mapped to one or like mapped to no lines in the ground truth. And clearly there's exact match, which means the predicted edits is exactly the same as the ground truth edits, which we think is good, and we don't need further tests. But there are possible like different edits that are also true, also semantically correct. So we need to apply these blocks by replacing the matched lines in the ground truth edits by this block. And then we do a semantic test with the same set of unit tests. And if the block passed the unit test, we think this block is a semantically correct edits. But now, okay, we've noticed, okay, there's edits like in block 3. This is a big block across line 7 to line 12. This is semantically correct, but there's a lot of redundancy in it. So we use a redundancy check by selecting all the possible subsets in this blocks, possible subsets of line edits in this block to find the minimum set of correct, semantically correct edit and that satisfy the passing condition for unit tests. And in this example, we find like line 10 to line 12 is the actual correct edits.
So how do you figure out where the block boundaries are?
The block boundary?
Yeah.
They're continuous, like just like separate.
You're just predicting block boundaries?
You mean how do we?
Why do you say that block 2 starts at line 4 and that block 3 starts at line 10?
Oh, there's a mapping algorithm. We use nearest neighbor like variations to match this.
Wait a second. Actually, I'm sorry. It's block 2 starts at line 4 and block 3 starts at line 7.
Block 2 is matched to line 4 because it's editing
Right.
line 4. Yes. So block 3 is.
Sorry. Oh, this is just based on when things change.
Yeah, this is just based on
Okay.
where.
I'm just kind of I'm a little confused because you're doing these things like semantic check and redundancy check, and like when you look at block 3 in this example, but there's probably other examples like this, it's not a semantically coherent unit because it has like the end of an if statement but without the test, right? So like if you looked at that block by itself, it's hard to kind of analyze it at all, it seems to me, right?
Yes, but this is the best thing we can do.
Sure, because you get to a point where you kind of can't even decompose things.
Right. So if we think of there's so our assumption is like we are for block edits you always edit like one bug or a few bugs, right? You don't do don't do like separation edits of different things and to fix one bug. That is considered as regeneration for sure.
Right. I mean, like specifically with block 3, right? Like you have an assignment to R, right? But like there is no consequence revealed within block 3, right? That consequence comes out of line 4. So it seems like unless you have the context of the blocks, it seems like you could never, know whether or not line 7 is correct because you're not doing any kind of test on it, right?
We are doing because we will select like smaller blocks. We will select like a line 8 to line 12 and line 9 to line 12.
Yeah, but unless you have line 4 through line 7, then you can't understand the relationship between what you do to R and its impact on the entire algorithm, right?
We match the block based on the so I'll talk about this matching a little bit more. So we match blocks based on there's similar lines in before it and similar lines after it. So we make sure this block of edits is mapping to line 10 because there's similar lines in the that wraps it. So there's a wrapping around it, like yeah.
I think out of the interest of time, we should move.
Sorry.
Okay. Yeah. Just like yeah. On the high level, after all these checks, we find the semantic crack like blocks within the edits, and that block is semantically correct and passed unit tests. Now, like ideally, we want to have like the most precise edits is like one line, right? Because we only generate one line bugs. So the most precise bug is like one line edits reversely back. But we don't want to say, okay, we want this like very strict, because there are possible like 2 or 3 lines edits that is also a possible fix for one line bug. So we apply a tolerance of k equal to 3 for crack and minimum block edits. That means if your crack minimum block edits is 4 lines, we only consider 3 lines as the effective edits, and the 1 extra lines as unnecessary edits as rewriting. If your blocks minimum block is smaller than 3 lines for 1 bug, we consider it as good. So for this example, the precision is 4 lines over 8 lines marked in blue, and the recall is 2 over 2. But we introduce the debug introduce a new bug in line 2. So if we test on unit tests, it's a failure for this. Is it clear? Questions? Yep. And we created a benchmark called PDB hard by 2 existing coding benchmark, Big Code Bench and Live Code Bench. We generate 1 to 4 bugs as the buggy programs over 5 different categories. And it's not a surprise, but current language model remains far from achieving precise error-aware debugging. And we observe different model behaviors on debugging. So for the top models like Claude Sonnet 4.5 and Gemini 2.5, we view this model as pass with precision. So they're both high on the relatively high on precision and recall, as well as unit test score. And Queen's Recoder is slightly different. It is weak on the unit test score, not that high, 71, but it's the highest except the top models on precision and recall. And we have these 3 medium model, weaker medium models, which is weak, imprecise, but faithful. So they identify bugs, but struggles to produce crack and precise fix. By identify bugs, I mean the recall is greater than unit score. And finally, there's only example models that only care about pass, which is the model we want to punish the most, GPT 5.1 CodeS and DeepSeek families. So we also want to show agentic debugging, currently debugging the best agentic debugging, even in Cloud Code. They improved the unit test scores, but for precision and recall, they didn't improve as much. So in summary, we need a precise and error-aware debugging over all type of bugs for applying domain adaptive programming. And we want to shift the language model training evaluation pipeline on coding tasks from unit test focus to precision focus. This is the third part of my talk. And because the timing issue, I'll just briefly talk about my future directions. So first, I think we want to apply this neurosymbolic thinkings to more rigorous language model evaluation. We know we have language model as a judge for most of the tasks, but that is not not like precise and robust. And we want to have more tasks that can be symbolic verified and give a score. And currently we have like domain adaptive programming, but we have to give like very specialized prompt and specialized design to different domains like robotics, like embodied AI. We need to give like tasks different like specification on the domain, on what the domain is like. But can we have a more generalized domain adaptive programming which requires minimum or no human supervision on this? And finally, I think I'll always work on language model coding and debugging because this is the foundation of like a language model ability on generating program, and it's a foundation for neurosymbolic to work. Yes.
So yeah, I'm watching the Zoom for questions. I don't see any yet. I have one question on the previous project, right? On the coding thing, how do you manage for contamination? So this benchmark that you created, you start with coding benchmarks, then you introduce bugs, and then you measure their ability in some short way to reconstruct minimal edits, right? But if a language model was trained on the original benchmark, then it's going to be more likely to just resurface the original thing, right? So how do you know that the performance of like GPT-3, like Gemini 3 being better than GPT-5 Codex isn't just that the benchmarks that you use to source your test is one which Gemini has trained on more actively, and so it's more likely to reproduce those particular lines of code?
Very good question. Very good question. I think, okay, we also did an ablation, like check our paper. We will release it very, very soon. We rewrite the ground truth solution before we generate bugs. But that actually, so first, it keeps the same ranking.
Yeah.
Second, it makes the task even easier. Because we previously think, okay, the memorization is the issue of causing this unpreciseness. But we figure out this is not the issue. Actually, for language model generating the code this is, I think, the evaluation paradigm and the training paradigm is the issue. Because we did two tasks. One is we rewrite the ground truth solution with the same bug generator language model, and second is we swap it. We use a different model to generate a bug and rewrite it. But they are all the same. Like, yeah, there's a table in the paper.
Thanks very much.
I don't think I see any questions on Zoom. So yeah, I think we can close. Thank you.